Today we're going to start our race to the finish unit, which is our next to the last unit, water, aqueous systems, acid base, and pH calculations. First of all, let's define what a solution is. A solution is a homogeneous mixture of two or more substances in a single phase. In a solution, you have two main components, a solute and a solvent. The solute is the substance being dissolved. It's going to be the substance that is present in the least amount. The solvent is the substance that is doing the dissolving. It's the dissolving medium, is what they call it. It's going to be the substance that's present in the greatest amount. Now make sure when you're looking at your amounts, you're using the same unit, like if you have the mass or you're comparing the moles. You must compare like units. Now there's a rule of thumb for solubility, meaning there's a rule that you can kind of follow, a general rule that will work for as far as if something will be soluble in another substance. And that rule of thumb is like dissolves like, meaning substances that are alike in their chemical bonding will dissolve other substances like them. So like a polar molecule will dissolve a polar substance. Nonpolar substances will dissolve nonpolar substances. But polar will not dissolve nonpolar. So that's why oil and water do not mix. Water is a very polar molecule. Oils and fats, those are nonpolar in their molecular structure, so they would not mix, no matter how much you stir them. There's three things that you can do to speed up the dissolving process. You can shake it or stir the substance, the solution, and when you do that, the particles of the solvent and solute collide more often, and therefore you would increase the number of collisions between the particles, and the mixture would dissolve into a homogeneous solution more quickly. You could also heat it. If you increase the temperature, that increases the kinetic energies of the particles, and thus the collisions of the particles are going to occur more frequently, and so therefore it will dissolve. This is all based on a theory known as collision theory, which simply states that in order for particles to react, they must collide, and the more often they collide, the faster the reaction will take place. The third thing you can do is you could crush the substance into tiny particles. By crushing the substance into tiny, tiny particles, it increases the total surface area of the particles. So therefore, the solute can be surrounded by more of the solvent, and therefore it will dissolve faster. This is a solubility curve, an example of a solubility curve, and you also have a handout with a separate solubility curve on it. So what a solubility curve shows is it's a graphical representation of the solubilities of various substances over a range of temperatures. Here on this particular graph, let's just kind of look. It says, describe what happens to the solubility of potassium nitrate as the temperature increases. So as you can see, the potassium nitrate curve is this purple curve. So I want you to describe what happens. So notice as the temperature is increasing, the solubility of the potassium nitrate increases as well. So they're directly proportional. B says identify which substances show a decrease in solubility as the temperature increases, and then which substances exhibits the least change in solubility as the temperature increases. Well, let's answer the first part. Decrease in solubility. Well, you would be looking for the curve that has a negative slope. So this lime green curve here has a negative slope. So the ytterbium 3 sulfate would be the one that you would answer for the first part of that. And the substance that it has the least change in solubility over the temperature changing would be here this orange colored for the sodium chloride. Notice it has almost zero slope. Now if I were to ask you specifically what is the solubility of potassium bromide, okay, so there's your green line, at, let's say, 40 degrees Celsius. So you would find 40 degrees Celsius, you would read up to where it intersects the green line. And notice it's right below 80. So let's say it was like 78 grams of potassium bromide would dissolve in 100 grams of water. Notice here solubility is defined as the grams of the solute per 100 grams of water, and water being your solvent here. There are two ways that we express concentrations of solutions, molarity and molality. Molarity has a symbol, a capital M, and we can use that for its unit. And molality has a lowercase cursive italicized M for its symbol. We're going to first look at the formula for molarity. Molarity is defined as the number of moles of your solute divided by the number of liters of your solution. Now remember, your solution is the solute plus the solvent. That's what a solution contains, solute plus the solvent. Moles of solute divided by liters of solution will give you the molarity, and we call these molar solutions. And we're going to come back in a separate video and we're going to do these examples, but I want to go ahead and get the molality formula copied down, and then I'll do a separate video with some calculations. Molality has a lowercase italicized cursive M. These are called molal solutions. Notice both of these words sound very similar, molarity, molality. Also notice their formulas are very similar with respect to their numerator. Both formulas have the number of moles of your solute in the numerator, molarity and molality. Here we're dividing by the number of kilograms of the solvent though. Just the solvent, not the whole solution. And remember, water is your universal solvent. So if water is your solvent and they happen to give you the volume of it, then we can use this relationship. 1 kilogram of water is exactly the same as 1 liter of water, and 1 gram of water is exactly the same as 1 milliliter. Now in our next video, we will take a look at how to use these formulas and manipulate the equations to solve for moles, for grams, and for molarity and molality.